Well, hello everyone. Assalamualaikum warahmatullahi wabarakatuh. Today we're going to learn about Phasor diagram plus explanation about impedance, resistance, and reactance. Well, why did we use it? Phasor diagram. Because we have to make analyzing AC circuits easier, as we know that AC circuits will result a sinusoidal quantity, and so that's why we have to analyze each part of quantity in AC circuits, including current and voltages. Second, instead of comparing sine waves as a sinusoidal quantity, you can just compare arrows and their angles. Like here, we have a Phasor diagram, a simple one. We have Vmax as the maximum signal for voltage, and we can project onto the x-axis, so we have V, the real value at one time, at a specific time for voltage. That is equal to Vmax times cosine omega t, and omega t as the angle of this vector. Okay, as we know that Phasor diagram is a graphical way to represent sinusoidal quantities like AC voltage and current as rotating arrows or vectors instead of wavy curves. Okay, first of all, actually Phasor diagram is not really representing a vector, but this is only a graphical way to represent the complicated sinusoidal quantities. As we know that sinusoidal quantities hasn't a specific values. It will always vary from the maximum value to the minimum value. So we have to analyze it using Phasor diagram. Engineers use Phasor diagram to quickly see whether current is in phase, leading or lagging voltage. Hands-on, we will learn about how this Vmax will be different to the other kind of component in a circuit. For example, in a resistor, the voltage will be different in phase to the inductor and resistor. Okay, first of all, we know that here V is equal to Vmax cosine omega t. So because V is parallel to the value of current, so current will be also equal to I max cosine omega t, like this. Okay, now we will see the correlation between every components in a circuit that we have learned in DC circuits, and how if we apply every component in DC circuit into the AC circuits, as we know that we have already learned about resistor, inductor, and also capacitor. Okay, we start from the resistor. Now we see here that we apply a resistor in an AC source like this, and there will be a signal as well. There will be a signal right here. Let's say that this is a current, and the current will flowing through this resistor. And here we will analyze using the Phasor diagram and also in Cartesian diagram. Okay, first of all, as we know that in Ohm's law, we know that I is equal to voltage divided by resistor. Then previously we know that V is equal to Vmax cosine omega t, and now we have to divide both by R, so we're gonna have I in here, then Vmax divided by R, it's gonna be equal to I equals I max cosine omega t. And here we have two different formulas for different quantities. Okay, first we have voltage, yeah, which represented by V max cosine omega t, and I represented by I max cosine omega t. And we know that these signals, both signals, are in phase. Yeah, if we create a Phasor diagram, so we can create, okay, that this is I max, and this one, or maybe we can just use I, yeah, instead of I max, so we can understand this concept easier. And one more is V. Now we can see that the signal for I and V is in phase. Yeah, because we know that there is no angle of phase in this cosine omega t. There's no theta something, or yeah, something like that. So that's why when we create signal in a sinusoidal wave, because this is cosine omega t, so we would start from the maximum values. Let's say like this. Okay, I'm sorry. Okay, like this. And this one is I, yeah, the signal of I. And then the second one is V, the signal of V. So we're gonna have this with different values like this. Yeah. Okay. To understand the differences between both signal are in phase, lagging or leading, so we can see the next component of AC circuits. Well, as we know from Faraday's law in electromagnetic effect, when there is a current flows through the solenoid or an inductor, there will be an electromotive force resulted from that phenomenon, which represented by this form: V equals L times di per dt. L itself, this is an inductance of an inductor, right? And as we know previously that I is equal to I max cosine omega t, and we can just input it to the formula. So we have L times di max time cosine omega t divided by dt. And here we have I max as a coefficient which has a constant values, so we can just take out from the derivation process. Then we have d cosine omega t divided by dt. So we have L I max times minus omega sine omega t. Okay, this is the result from this derivation process. So we can restructurize this form into I max L times omega minus sine omega t. And as we know that minus sine omega t, it can be turned into cosine omega t plus 90 degrees, right? So we're gonna have I max L omega times cosine omega t plus 90 degrees. Okay, here, focus. We have 90 degrees behind the omega t. Yeah, so this is actually the phase, the V, or the voltage resulted from an inductor, right? Let's say that Phasor diagram is this one for the voltage, right? Let's say because this is an inductor, so we can symbolize by VL, and then we can see here that the values of V is plus 90 degrees. So it means that the voltage is leading the current. Okay, so we can draw the current with different color maybe as this one. This is IL, or the current in inductor. Yeah, we can see here that the phase are different for both signals. Okay, for drawing a diagram or a sinusoidal wave for voltage and also current will be represented by this signal. Wait a minute. Okay, first we can start from the I, okay, the current. Okay, first of all, the current, we have this signal because it's only, sorry, okay, this is I. As we know that I is equal to I max cosine omega t, so this is I max, yeah, this one is I max, actually. Yeah, but maybe we don't need to draw it, okay? And then for the voltage, because the cosine is cosine omega t plus 90 degrees, so it leads the current. Okay, maybe we can just use the minus omega sine omega t, as we know that sine is start from 0, and because it's minus sign, so we start from the downward direction 1. Okay, this is, let's say that, okay, like this, peak, and then 0 again, peak again, 0 again, peak again, 0 again, peak again, 0 again, and peak again. So this one is voltage, and we can see here that the signal both are different. Okay, so we can say that voltage leads the current. Okay, or reverse, the current lags the voltage, like that. Okay, third is capacitor. Okay, let's say we have an AC circuit which has capacitor components here. The AC source will generate a current, an AC current like this, and the AC current will flow through the capacitor. Then as we know that I itself is equal to dq per dt, or the change of charge per time. And then using the integral concept, so we're gonna have dq will be equal to I dt. Then we have an integral 1 that q is equal to integral of I dt. I, from our first equation, that I is equal to I max cosine omega t. So we're gonna have integral of I max cosine omega t dt. Then, because I max is constant, so we can just take out over there. So the rest is integral of cosine omega t dt, right? Then I max cosine omega t dt will be equal to sine omega t, yeah, times 1 per omega, yeah, because this is integral, right? So this is actually the Q. Okay, we can restructurize. Then we have I max divided by W, or omega sine omega t. Okay, then as we know that capacitor has formula of capacitance that is equal to Q divided by V, charge divided by the voltage, and V will be equal to Q divided by C. So we can just input this quantity into this form. So we're gonna have I max sine omega t per CW. Well then, as we know that sine omega t is equal to cosine omega t minus 90 degrees. So we can see here that there is a change in the phase of the signal. So we're gonna have I max cosine omega t minus 90 degrees, okay, and divided by C omega. So first of all, we have I as I max cosine omega t here, and now we have voltage as I max divided by CW cosine omega t minus 90 degrees, right? Okay, first we can redraw the voltage. Okay, we have the voltage. Let's say that the voltage is right here. This is VC, yeah, to symbolize the voltage in capacitor. And then we're gonna have IC, which is leads the VC, yeah. Okay, we have IC right here, yeah. And why the IC is leading from the VC? Because we know that here the V signal or the voltage signal is legs. It represented by this minus 90 degrees. Yeah, so this is legs. Okay, so VC legs the IC. Yeah, the voltage in capacitor lags the current in capacitor. Yeah, it different from the inductor. The voltage leads the current, but in here the voltage lags the current. Okay, then we're gonna have a signal for VC first, and maybe I first. Okay, I is still the same as before, like this, right? And then for the voltage, wait a minute. This is IC. Okay, and then for the voltage or VC, it started from sine omega t. It started from the sine omega t. So it means we start from 0 and we draw it upward first. So we're gonna have this as the peak values, and then downward 0, big value again, 0 again, peak value again, 0 again, peak, 0, peak, 0, peak, 0, and then this is VC that lags the IC, right? Well, next is impedance, a new term in AC circuit. Well, impedance means total opposition that a circuit presents to the flow of current when a voltage is applied. Impedance itself actually exists in DC circuit, as we have already discussed earlier about the Ohm's law and the other concept in DC circuits. Okay, well, impedance means that this is a general form for resistor, because in here we also account the effect of inductor and capacitor, because inductor and capacitor store an opposition process as well as the resistor. Okay, and impedance, this is symbolized by Z. Well, Z itself, when we remember again to the Ohm's law. So we're gonna have V, which is equal to I times R, or I is equal to V divided by R, right? And in here, because we only have an R as the impedance, and now we can generalize this form into V equals IZ, or I equals V divided by Z. So we have an impedance form of Ohm's law. Well, let's continue. From previous discussion, we already know that Ohm's law is represented by V equals IR, or I equals V divided by R. Then let's have a look to resistor component, but in AC circuit. So we're gonna have the final form for V signal and I signal will be equal to I max times R cosine omega t. And because both VR and IR are in phase, so we're gonna have IR as I max cosine omega t. And here we have I max times R, which is equal to VR max, and IR is equal to I max. Okay, let's focus only on this form. We have I max R, which is actually represented the value of VR maximum based on this Ohm's law. But let's have a look to another form of component. Let's say we have an inductor which has L as the inductance. So we're gonna have the final form from our previous discussion that VL is equal to I max L omega times cosine omega t plus 90 degrees, right? We know that the current for the inductor component is the same as the resistor component. This is IL equals I max cosine omega t. And here we have a different phase angle for the current and the voltage in an inductor. So we can say that they are in different phase, or the voltage leads the current. Okay, then I want to spotlight on this side first, LW. And as we know from the previous one, we have VR times I max times R, and R in here positionized as an opposition in resistor. And here we have LW. Yep. And this is also an opposition in an inductor, but in here we call it as resistance. Yeah, and in here we can call it as an reactance, the quantity of opposition in an inductor, and we can symbolize by XL, which is represented an inductive reactance. Well, inductive reactance because it's only appeared in inductor. Then let's have a look again to the capacitor component. From our previous discussion again, we know that Vc is equal to Imax divided by omega c times cosine omega t minus 90 degrees. Okay, and then for the current, it will be the same as the previous one. So it's IC times Imax cosine omega t. So we're gonna have Vc that likes the IC. So it's the reverse version from the inductor, right? Because in inductor we have VL leads the IL. So, but in C, in capacitor, we know that VC lags DIC. And then let's spotlight again to the opposition part of this equation. Okay, from this equation, the opposition part is from this one. Okay, so this one is actually Xc, which is represented capacitive reactance.